Hi guys, in this video I'm going to go over the exam review questions. Alright, let's start at the beginning. Right. Suppose 20 people play a game which each draw 2 cards from a full deck of 52. They record the identities of the cards but not the order. Alright, that's important. What's the probability that at least 2 people draw the same pair of cards? Well, this at least 2 indicates immediately that we probably want to flip this probability on its head and compute the opposite. So the opposite, or rather the complement of at least 2 people doing something is that none of them do it, and that's generally easier to compute. So the complement here is that nobody draws the same pair. That's an easier probability to compute. Alright, so how might we compute this? Well, let's think, how many options does the first person have? So the first person, there are no constraints since they're the first to go, so if we're trying to constrain that nobody draws the same pair, the first person could draw whatever we like. So there are 52 cards, we're drawing 2 of them, and we're not counting the order that they're drawn, just the set. So what we're counting is sets of 2 from a set of 52. So that's, by definition, 52 choose 2. Second person, if we want to make sure that nobody draws the same, the number of possibilities there is going to be 52 choose 2 minus 1, because they can't draw the same pair that the first person drew and still, for the outcome to be in this event. Alright, third person, right, is they have 52 choose 2 minus 3 possibilities, and so on. The last person, so the 20th, we have 52 choose 2 minus 19. Alright, so the probability that nobody draws the same pair equals, well, it's the product of all these things, since all of these things have to be true simultaneously. Well, that's not really the right reason. The reason is the number of ways that we can have 20 people draw these pairs is the product of all these, by the counting principle, or the multiplication principle. So we have 52 choose 2 times 52 choose 2 minus 1 times 52 choose 2 minus 2, and so on, up to times 52 choose 2 minus 19. And we divide by the number of ways it's possible to draw 20 pairs without any constraints, and that would just be 52 choose 2 to the power of 20, just making that choice 20 times. Okay. So this is 1 minus the probability that we want, since this is the complement of the situation in which at least 2 people have the same. We can also rewrite the numerator. Easier way to write this is simply 52 choose 2 permute 20. So this is permute 52 choose 2, comma 20, which is a slightly new situation in that we have our nested combinatorial functions, but there's nothing wrong with that. So what we get in the end is that probability at least 2 people drew same pair equals 1 minus 52 choose 2 permute 20. That should be a 20. So 52 choose 2 permute 20 divided by 52 choose 2 to the power of 20. And that is roughly, I did this calculation, that is roughly 13.4%. So it is roughly 0.134. Alright, on to the next one. So, 2 4-sided die are rolled and their sum recorded. Compute the probability distribution of this experiment. Alright, well, if you're asked to compute a probability distribution, the first thing is to figure out what the sample space is. So, sample space. This is the possible sums of the die. So the lowest is if they're both 1, and that gives us 2. And we can have anything up to 8, as that's when they're both 4. All right. Now, in general, so two 4-sided die can be tossed in, well, there's 4 options for the first die and 4 options for the second die. So 4 times 4, that's strange, 4 equals 16 ways. So 16 is generally going to be the denominator when we're computing our probabilities. So to get 2, they both need to be 1. So there's only 1 out of 16 options that give us a sum of 2. So we have 1 over 16. All right. So for 3, we could have 1 and 2, or 2 and 1. So there's 2 ways that can happen. So that's 2 out of 16. For 4, right, we have 2 and 2. We have 1 and 3, or 3 and 1. So that is 3 ways, so 3 out of 16. For 5, let's see, we could have 1 and 4. We could have, of course, 4 and 1. We could have 2 and 3. Or actually, I'll put it next to it. 2 and 3, or 3 and 2. So that gives us 4 out of 16. We could be simplifying these fractions if we want. This is 1 over 8. I can't simplify that one, but this one equals 1 over 4. Alright, moving on. We're halfway done, or a little more than halfway done. 6. Well, we can't have 1 and 5 since these are 4-sided die, but we can have 2 and 4, and thus also 4 and 2. We can have 3 and 3, and that's it. Those are all the ways. So this is again 3 out of 16 equals, yeah, no, there's no simplification there. To get 7, we could have 3 and 4, or 4 and 3, and that's it. So this is 2 out of 16. And lastly, 8, we could have 4 and 4. That's it. So we have 1 out of 16. Alright, so to be neat, what we can do is put this all in a nice little table of the outcome and the probability. We have 2 has probability 1 out of 16. 3 has probability 2 out of 16. Actually, let me remove these, they're annoying. 4 has probability 3 out of 16. 5 has probability 4 out of 16. 6 has probability 3 out of 16. 7 has probability 2 out of 16. And lastly, 8 has probability 1 out of 16. Actually, I kind of need them. Alright, and one thing we can do to check is that make sure this whole column here, all these numbers, all the probabilities must sum to 1. And you can check that they do. Alright, so that's question 2. Question 3. Suppose that a small town of 1,200 people, one person is chosen at random every day and wins a small lottery. It is implied that each day the random choice is independent from the previous choices. What is the probability a specific person is chosen at least once in a given year? Well, again, this at least business, since we're not being precise, there's a lot of ways you could be chosen at least once. You could be chosen exactly once, you could be chosen exactly twice, you could be chosen exactly 3 times. And if you're chosen exactly 3 times, for example, there's a lot of different ways you could do that. 365 choose 3 would be the number of ways you could be chosen exactly 3 times. That's a 3 different, how many different sets of 3 days could there be? And that's big. And we'd have to go through all the possibilities up to 365. So we have this at least once. What we probably want to do is compute the probability of the complement. So what is the complement? The complement of getting chosen at least once is getting chosen no times. So never chosen. Now here's where the independence comes in. So we want to compute the probability of a specific person. So probability specific person is never chosen. And to be never chosen, they have to not be chosen every day. So, and because they're independent, having a bunch of decisions that all must be true simultaneously, we can just multiply the probabilities together. So this equals probability not chosen on day 1 times probability not chosen on day 2 times, etc. up until probability not chosen on day 365. Alright, now it's the same process each time. They're just being chosen at random from 1,200 people. So this just equals probability not chosen on a given day to the power of 365. Alright, so what we need to do is figure out what the probability of them not being chosen on a given day is. Well, it's 1 minus the probability of them being chosen. So probability not chosen on a given day equals 1 minus the probability that they are chosen on given day. And the probability that they are chosen is just 1 out of 1200. So this equals 1 minus 1 over 1200. If you do a little rearranging, that's just 1199 out of 1200. So then our final answer then is 1199 out of 1200, all to the power of 365. What does that equal? That equals, right, this, right, sorry, this equals roughly 0.7376. And so then the probability that they are chosen at least once is the complement of this. So then probability chosen at least once equals 1 minus 1199 over 1200 to the 365, roughly equals 0.2624. And that's our final answer. Okay, on to the next one. So consider the Venn diagram, A and B. So we want to compute the probability of B given A, the probability of A and B, and then there's a part C. Let's just do these first. So probability of B given A. Well, this equals the probability of A and B, or A intersect B, divided by the probability of A. Alright, so the probability of I guess the question is very terse, but what we should assume to be going on is that a random thing is being chosen, and the number of things in set A is this, the number of things in set B is this, and so what we mean by the probability is the probability that this random thing belongs to set A or belongs to set B. Yeah, I mean, I just was too lazy to come up with a story for this example. But so the probability of this random thing belonging to A and B is simply the size of A and B, which is 10, divided by the size of the universal set, right? So that's, if we add this up, 10, 10 is 20, plus 40 is 60, plus 40 is 100. So this equals 10 over 100, divided by the probability of A, which is 50 over 100. And that equals 1 over 5. Alright, so to compute the probability of A given B, well, it's just the same thing again. Probability of A given B equals probability of A and B, so the numerator is the same, but now we divide by the probability of B. So this is 10 over 100 divided by the probability of B, which is 20 over 100, and this equals 1/2. Okay, so now the next question, the next question is, are A and B independent events? Justify your answer. So we can't just give a yes or no, we have to show the computation that tells us is what that means. Well, what is probability of A? Probability of A is the size of A divided by the size of the universal set. That's 50 over 100. Getting a phone call. Alright, sorry about that. Okay, 50 over 100. Now probability of B equals 20 over 100, the size of b. Alright, so the probability of A is 1/2, and the probability of B is 1/5. These fractions look familiar. So then, right, we have the probability of A and B equals 10 over 100, as we've used before, which equals 1 over 10. And this equals, of course, 1/2 times 1/5, which equals the probability of A times the probability of B. Alright, if the probability of A and B is equal to the probability of A times the probability of B, that's the definition of them being independent, so yes. If the numbers were even slightly different, then they wouldn't be independent events. Alright, on to the next one. So consider a group of 1,000 people in which 600 believe in a heliocentric solar system and 400 believe in a geocentric solar system. So they probably wouldn't call it a solar system if they thought that the Earth was at the center of it. Maybe they call it a geosystem. I don't know. All right, so we randomly select 10 people from this group. And what is the probability that this random sample contains disagreement? So it contains some people who believe each cosmic view. Well, as has been the theme, the easiest way to do this is to compute the probability of the complement. And that there's a lot of different ways you could have disagreement, but there's not a lot of ways you could have 100% agreement. So easier to count ways they could all agree, which is the opposite. So, well, there's really only two ways. So it would be the number of ways that they would all be heliocentric, plus the number of ways they could all be geocentric. That's the number of ways that they could all agree. All right, so then the probability, would be, they would then divide, so then the probability, well, we'll get to that. So how many ways can we choose 10 where they'll all be heliocentric? Well, there's 600 and we're choosing 10 people. So the number of ways to do that is 600 choose 10. So you have 600 choose 10. That's the number of sort of interview samples where they all believe a heliocentric solar system, plus the number of ways we could choose 10 people who all think the Earth is at the center of the solar system. So then that would be 400 choose 10. Right, so that's the number of ways they could all agree. So the probability of this happening would be then dividing by the number of ways we can choose 10 people in general from 1,000. So that's just divided by 1,000 choose 10. All right, so this is this fraction, right? That's the probability all agree. And what we want is the probability that some of them disagree. So what we want is 1 minus this. So this is the probability there is disagreement. Equals 1 minus the probability that they all agree. If you plug this into a calculator, you would get, so 0.9939. So the probability that there's some disagreement is extremely high. Okay, 6. Suppose you have an unfair coin that has a 60% probability of coming up heads and a 40% probability of coming up tails. You flip the coin 10 times. What is the probability that the sequence you get contains both heads and tails? This is from a strategic perspective. This is very similar, although the formulas are going to be very different. If it has to have both heads and tails, again, it's easier to count the complement, the probability that it's either all heads or all tails. So again, so probability of both heads and tails equals 1 minus the probability all heads, all H, or all T. And the probability of all H or all T is just the sum of the probability all H plus this, so it's the probability of all H plus the probability of all T. Okay, so what is the probability that if we flip a coin 10 times, it'll come up heads every time? Well, initially that would be 1/2 to the 10, but that's for a fair coin. We have an unfair coin, so the probability of coming up heads is 60%. So this equals 1 minus the probability of getting a head, then 10 times in a row, plus the probability of getting a tail 10 times in a row. Alright, you plug that into a calculator, you'll get roughly 0.9941. So this is actually very similar to the number we got previously. And part B is sort of asking why that would be the case. So why is the number similar to the previous problem, and why is it not exactly the same? Well, the formulas we got were completely different, but as we've seen, sometimes you can have very different formulas that give you the same number in probability and counting, but these give you very similar numbers, not exactly the same number. So why is that? Well, this is just completely just talking about like intuition of the situation. So imagine, so choosing a single person from the crowd, right, of 1,000. The first person you choose has a 60% probability of being heliocentric and a 40% of being geocentric. So that's actually the identical situation to flipping our unfair coin. It had a 60% probability of being heads and a 40% probability of tails. The identity of the first person you choose is 60% one, 40% the other. So that's initial similarity. So then the question is, well, why, maybe if we choose 10 people, why isn't that the same as flipping a coin 10 times? They're not exactly the same, because when we choose the second person, right, we make 10 choices. So choosing the second person, and the second person can't be the same as the first person, because we're choosing a group of 10, not the same person 10 times. Second person, the probabilities are going to be slightly different. And why is that? Are slightly different. Well, if we chose a heliocentric person the first time, then there's only 599 heliocentric people to 400 geocentric people. So we'd have 599 divided by 999 would be the, well, that doesn't look like a 999. 999 is the probability of being heliocentric. And we'd have 400 over 999 is the probability of being geocentric. So these are very close to 60% and 40%, but they're slightly different. And each time you choose another person, the probability changes again slightly. So only the first person is exactly the same as flipping this unfair coin, and after that the probabilities change slightly because you're modifying the group that you're choosing from by choosing them and not replacing them, right? Because you're choosing them and then you're choosing from everyone else who you haven't chosen yet. But if you had, 1,000,000 people, then probably for all, intents and purposes, even if you cared for, really, really precise answers, you could probably model this as kind of flipping a coin, because each person you choose has such a tiny effect on the overall makeup of the rest of the population. That's kind of an aside, but I thought it was kind of interesting. All right, let's go on to the next question. So 7. A multinational corporation has 3 divisions, A, B, and C. The percentage of bilingual employees in each division is given by the table below. So on division A, there's 500 people, and the proportion of bilingual is 6%, B, 903%, etc. All right, what is the probability that a random person is bilingual? All right, so that's simply number of bilingual employees divided by number of people in total. So that just equals the number of bilingual employees from division A, so 500 times 0.6, plus the number of bilingual from division B, so 900 times 0.03, 06, not 6, plus 800 times 0.04. All right, we divide by the total, so 500 plus 900 plus 800, well, we could just do that. 500 plus 900 plus 800, you know how I struggle with arithmetic. I think that comes out, well, let's see, 500 plus 900 is 14, plus 8 is 22. So this roughly equals 0.04. All right, 0405, let's say. Okay, all right, so 4.05%. Now, what is the probability that a random bilingual employee works for division A? Well, so let's say L is the event that the person is bilingual, and A equals works for division A. All right, so then what we want is the probability that they work for division A given that they're bilingual. Well, this is a good time to use Bayes' theorem and not a tree diagram. So this is going to be the probability that they work for division A times the probability that they're bilingual given that they work for division A, divided by, on second thought, I'm going to move this down so that I have, so that I have room. All right, so divided by all the different ways they could be bilingual, right? Which is actually what we computed before, so it's just this number. So 0.0405. And that comes out to be, actually I didn't calculate this beforehand, so I'm going to need to do this real quick. So we have the probability they work for A is 5 over 22 times 0.06, and then divided by 0.0405. That equals 33, roughly, 0.337%, or rather 33.7%. So it's roughly a third of the bilingual employees work for division A is what this is saying. All right, seems about right. so then we have our last problem. So two people, P1 and P2, are playing a game. There are 4 beads on the table between them. When it is their turn, a player flips a coin. If it is heads, they take 2 beads, and if it is tails, they take a single bead. If there's only a single bead left, then regardless of what they flipped, they take both beads. Or sorry, if there's a single bead left, regardless of what they flipped, they will take the bead. Alright, so the player to take the last bead wins. Player 1 starts. What is the probability that player 1 wins? And so this is definitely a case when we need to use a tree diagram, as it's going to be kind of complicated. And they're using a coin flip, so it's heads and tails, but what I'm going to do is I'm just going to mark the number of beads that are left so we can easily keep track of that. And we'll know that to the left we'll be taking away 2 beads, and to the right we'll be taking away 1 bead, and that they're each 50%. So we start with 4. Right, so player 1 goes, and they either take away 2 beads, which would leave 2 beads, or they take away 1 bead, which would leave 3 beads. Right, and these are 50-50 probability. This was player 1's turn. Now it's player 2's turn. Alright, so if there's 2 beads and they are lucky, right, they will take away 2 and get 0, or they will take away 1 and leave 1. So then these are 50%. If there are 3 and they take away 2, then they're left with 1. If there's 3 and they take away 1, they're left with 2. These are also all 1/2. Alright, and so the player to take away, this is player 2. So this was over here, right? When there's 0 left, that means player 2 won. So the game ends. Alright, so let's look at the remaining possibilities. So if there's a single bead, it doesn't matter what player 1 flips, they're going to take it. So there's only one option, and that goes to 0, and that is probability 1. Same over here, it's probability 1. If there's 2 beads, you could either take both of them and be left with 0, probability 1/2, or you could only take 1, also with probability 1/2, and be left with 1. So this is player 1 again. Alright, so player 1 wins in these 3 scenarios, so the game ends. Then the last scenario, just to complete the tree, right, is that we have player 2 goes, and whatever they roll, they have probability 1 of taking the final bead, and there's 0. And so then player 2 wins again. Alright, so now the probability that player 1 wins is the probability of these any of these 3 win conditions happening. So the probability of this one is, let's say, it would be 1/2 times 1/2 times 1. So that just equals 1/4. And we have the same probability for the next one, 1/2 times 1/2 times 1. So that equals plus 1/4 plus, then the last win condition is 1/2 times 1/2 times 1/2 is 1/8 plus 1/8. So this equals 1/2 plus 1/8 equals 0.625. That's our final answer. And so what this means is that player 1 has a slight advantage in this game. It's not a fair game. It's not really a game in a game theoretic sense. It's just a dice rolling thing, but we can call it a game. Anyway, that's the last problem. I hope this was useful. Email me if you have any questions, and good luck studying for the exam.